So, okay, now it's being recorded, and I'm going to share the screen. Okay, do you see it okay?
Yeah.
Yes.
Okay, good. So let's get started with the lecture. So logistics, we have an office hour today at 5. I will post the homework problem later today, and the discussion section again on Thursday. And these two subjects, CFT and dictionary between gauge theory and fiber bundles, are the things people brought up the last week, and we didn't get to them. So these are leftover subjects. If there's anything new beyond them, then let me know. So, I'd like to talk about QCD, but a little bit different approach from the Peskin-Schroeder. I would rather talk more generally about dynamics going on of gauge theories than specifically on QCD, which is the particle physics subject. And the particle physics aspect, of course, should be covered by in a different course on standard model by Lawrence. So I'd rather focus on aspects of dynamics of non-ordinary gauge theories in general. So before getting into dynamics, it's just one little the review of mathematics. So some of you actually brought up a question about adjoint representation, and I did not talk about this so far. So maybe this is actually a good moment to give you a little bit an explanation about this. So we all know that the generators of a Lie algebra have these commutation relations specified by the structure constant FABC. So these commutators, just like in commutators in quantum mechanics, always supposed to satisfy Jacobi identity, because if we have this double commutator and sum them up in a cyclic permutation, it's identically zero. So if we just write out these commutators explicitly as TB, TC minus TC, TB, and then further commutated with TA, and sum them up cyclically, then they're just identically zero. So that's the Jacobi identity. And we can also write out this Jacobi identity explicitly by using this definition of the structure constant. So the first commutator are written in terms of structure constant. Then you take the second commutator so that everything becomes now the second power of the structure constants. And this is summed over the generators E, because TE are linearly independent. So what that means is that this thing in the parentheses have to vanish. So that gives us a non-trivial identity among the structure constants. And so if you stare at this for a long time, and I move the third term to the other side of the equation, then you find that this is also can be viewed as a sum over the matrix multiplications. So if I view the first factor minus I FAED as a matrix TA of EC or ED index in this case, then this can be cast into the form of the matrix multiplications so that this TA, TB minus TB, TA is FABD, TD. And that is nothing but the adjoint representation. So I have not been very explicit about this, but the vector potential, field strength, ghost, anti-ghost, and this auxiliary field all are supposed to belong to this adjoint representation because they carry this index A. And the way the gauge transformation works on these fields in the adjoint representation is that the index A would be rotated to some other index, let's say B. So that forms a matrix on the space spanned by this index of generators. So if you're talking about SU2, then you have 3 generators. So you're talking about 3 by 3 matrix acting on these fields. And you know the 3 by 3 matrix for SU2 is the spin 1 representation. And that's nothing but the 3-dimensional rotation. And if you go to SU3, that's a case of QCD, then there are 3 squared minus 1, namely 8 generators. So the matrix will be 8 by 8. So these indices A, B, C, and so on run from 1 to 8. So this minus I FACD can be regarded as 8 times 8. So first 8 is C, the second 8 is D matrix for a generator A. So that's the 8 by 8 dimensional matrix that would satisfy the same commutation relation as this defining commutation relation of the Lie algebra. Hence, that can be viewed as a representation of the Lie algebra. And that is the adjoint representation. And when you take a trace of the generators on the adjoint representation, that defines this constant C2 of G. And I will tell you what they are in later today. But anyway, so this C2 of G is different from 1/2, which is what we had for the fundamental representation of SUN. So depending on what the group is, this number C2G will be different. But anyway, so this is just a quick overview of what adjoint representation is. We've been sort of using it implicitly, but I'm now putting it out very explicitly. So do you have any questions about this? Okay, and the Perkin-Schroeder, of course, has an explanation about this as well. So presumably many of you have already looked at it. Okay, and the C2 of G in mathematics literature is what is called the dual Coxeter number. So if you need to look up what these numbers are, then just search for dual Coxeter number, and there's even a Wikipedia page that talks about this, so you can find them. If you talk about this trace of the generators in general representation, we already introduced this notation C2 of R. And this number is called Dinkin index in math literature. So again, that's something you can look up. And I mentioned earlier that the normalization of generator is different between math literature and physics literature. In physics literature, the generator is a half of what mathematicians use. And because this trace is the second power in generators, the normalization is different by a factor of 4. So if you look up Dinkin index, then you have to divide it by a factor of 4 so that we can use it with the normalization that's common in physics literature. So anyway, so that's something you better know. So once you know the names, it's easier to look for them. So so that's why I'm actually mentioning them specifically. Okay, so let's first get started with what we think is the dynamics of the pure Yang-Mills theory, namely that no matter fields, just the non-abelian gauge field. And we already discussed the beta function. So this is the beta function at the one loop level. And the C2 of G, dual Coxeter number, is what we just discussed. And numbers are given in this table for all possible non-abelian gauge groups. And so you see the numbers. The whole point here is that, you know, they're all positive integers. So the beta function is negative for all non-abelian gauge theories without matter fields. So we call these theories pure Yang-Mills theories. So what that means is that, as we talked about already multiple times by now, the gauge coupling constant grows if you go to large distances or short at the lower energies. And so that's the behavior we see here. And this is where you see this, the fact that there is something called dimensional transmutation. So Yang-Mills theory has this gauge coupling constant up front. And this is the new normalization I introduced the last time. I rescaled the gauge field so that F mu nu now doesn't have any gauge coupling constant in it. And gauge coupling constant is only in front of the kinetic term of the gauge field. And so this is a common normalization people use in, for example, lattice gauge theory we talked about also last time. And this coupling constant is dimensionless. So classically, this theory is scale invariant. But in quantum theory, you have to introduce the cutoff or renormalization scale. So even though you specify the coupling constant as a dimensionless quantity, it secretly depends on the energy scale where you, for example, measure the coupling constant. And once you have a coupling constant defined at a particular energy scale, it runs and becomes stronger at low energies, and it blows up at some particular energy scale, which I called lambda. So in this context, lambda is not UV cutoff. This is actually the energy scale on the infrared side where gauge coupling constant becomes infinite. And so even though the theory classically is scale invariant, it ends up generating an energy scale. And that is the phenomenon called dimensional transmutation. And that's something I mentioned earlier in the context of the nonlinear sigma balloon 2 dimension. But what you see here is that pure Yang-Mills theory does the same thing. So the question is, when coupling constant seems to diverge, clearly perturbation theory doesn't work anymore. So it's actually a very non-trivial question to understand what exactly happens at this energy scale. Oh, by the way, any questions about this so far? Okay, good. And that's where the discussion we had, and that was the last part of the homework problem, comes in, namely that we believe the theory leads to a confinement. And so we introduced this Wilson loop on the lattice the last time. Here I'm defining it in the continuum space-time. So this is the loop integral of the gauge field. But because gauge field is a matrix form, they may not commute from one segment to another. So we need to introduce this path ordering, just like the time ordering we introduced in a time-dependent perturbation theory. So you first define a, let's say, rectangle, or in general, an arbitrary loop. And you successively multiply infinitesimal segments of this loop integral, and then go around the loop, and then take a trace, which I forgot to write. So Wilson loop is supposed to be the trace of this the link variable. And the idea is that when you actually do the path integral over all possible gauge fields with this Wilson loop inserted, then you can ask the question, how does this Wilson loop expectation value depends on the size of the loop? And we say the theory is confined if this Wilson loop behaves with the area law, namely that it goes down exponentially with the area of the loop. And area, of course, has the mass dimension -2, so it needs to be accompanied by a quantity of mass dimension 2, which is called the string tension alpha prime, because when you actually look at this area law and divide that into the distance in the spatial direction and the interval in temporal direction in the Euclidean space, then the area is simply L times T, so you can read off what the potential energy is between heavy quark and anti-quark, and so that actually turns out to be proportional to the distance, and hence this is the confining potential. So you can never liberate any objects with which are not invariant under the gauge symmetry, because the potential energy among them would grow linearly with the distance. So no matter how much energy you put into the system, you would eventually hit the potential barrier, and so that you cannot liberate the object. So that's the idea of the confinement. And I already shown you the results from numerical calculation on the lattice, how the linear potential does arise indeed from the non-Abelian gauge theory. And so the potential energy is supposed to be interpolation between Coulombic behavior at short distance, alpha S is the G squared over 4 pi for non-Abelian gauge theory, alpha S over R, where alpha S does depend on R. And so it grows like this, and eventually would be taken over by this linear behavior. And transition region is usually approximated by a logarithmic function. So it's 1 over R log and linear. So that's the expectation we have for the behavior of this potential energy in the Wilson loop. So in the limit where the loop is large enough, it shows this linear behavior, hence the area law. So this is what we regard to be the autoparameter to define what we mean by a confinement in gauge theory. And so we'll talk more about what actually happens when the theory is confined. So any questions about this?
So alpha prime is also dependent on R, right? Because G is running.
Well, so alpha prime is the slope of the potential when the distance is large enough. So that's the definition. So alpha prime is a constant. Okay. And because it has a dimension full constant, it is expected to be proportional to this scale lambda squared to get the right dimension.
Okay, okay.
Right. So what we normally call alpha is a dimensionless quantity, which is related to gauge coupling constant G squared over 4 pi. And that's not alpha prime. Alpha prime is dimension full quantity called string tension. Alpha is the G squared over 4 pi that's dimensionless. And alpha does run, as this curve suggests, by solving the renormalization group equation. But alpha prime is a slope, an asymptotic slope when the distance is large.
Okay,
it's a confusing notation.
And lambda, and you can extract lambda from that slope. That was my second question. But
so that's a good question. So based on dimensional analysis, alpha prime is supposed to be proportional to lambda squared, but it's not clear what exactly the proportionality constant is. And we can't compute it in perturbation theory because in a strongly coupled regime. So if you do the lattice calculation, you can compute it and determine alpha prime is 3 times lambda squared or 0.2 times lambda squared. That probably depends on what gauge group you pick. It's an order 1 constant, but we don't know exactly.
Okay, thank you.
Right? Yeah. Well, thanks for asking the question. So that's the basic idea of dimensional transmutation. So theory, classical theory that doesn't have any dimension full constant ends up generating the energy scale lambda. And that energy scale would correspond to the string tension, and the theory is supposed to become confined. And once the theory becomes confined, so this is what is believed, and there's no proof for it. So as I said already, gauge non-singlet states cannot be free. In particular, gauge boson itself cannot be free. And the lowest lying states in the system are believed to be what is called the Glueball. So the gauge boson, typically in the non-abelian gauge theory that becomes confining, is called the gluon, because it acts like a glue connecting everything that has a non-trivial gauge quantum numbers. So gauge boson itself belongs to this adjoint representation, so it has non-trivial quantum number on the gauge group. So the gluons will connect among themselves like this. And so the gluons become bound, and 2 gluons can become a gauge singlet, so that the 2 gluons can be liberated, but not a single gluon. So the bound state of 2 gluons is what is called the Glueball. And so then Glueball is massive. Again, that's a consequence of dimensional transmutation. So Glueball consists of 2 gluons. Each of them is massless. But nonetheless, the bound state is massive. And that's a dimensional transmutation. And we can compute the spectrum of the Glueballs in perturbation theory, because again, it's a strongly coupled system. So if you go to the lattice calculation, this is the kind of spectrum they predict. So the lowest state is 0 plus plus, and 0 is the spin of the system. And the plus, first plus refers to the parity, and second plus refers to the eigenvalue under the charge conjugation. And so the 0 plus plus is believed to be this lowest Glueball state. And you have various excitation states with different quantum numbers. For example, this one is 2 minus plus. So this is a parity odd combination of 2 gluons, but charge conjugation is positive, which means that this, roughly speaking, corresponds to an operator which has F mu nu and epsilon tensor, epsilon mu nu rho sigma, F rho sigma in it. And you combine them together to contract one Lorentz index, but leave the other Lorentz index uncontracted. And because it has 2 gluons in it, it's a charge conjugation plus. So in all of these cases, you can identify what kind of the operator you would write to create that state, which you can put on the lattice and compute their mass by looking at this exponential damping of the 2-point correlation function. And we talked about this before in the context of QCD. So that's the prediction. So all of these states made only of gluons, and they are just different ways that gluons can bind together. All of them are massive. So this is what is called the mass gap, namely that even the lowest lying state would have a mass which is different from the vacuum, the ground state. And the existence of this mass gap is what we expect to see in this pure Yang-Mills theory. Any questions about this?
Do the colors mean anything on here?
I don't know, I just copied from this paper. I think that this color are coded by the spins. So it looks like the red is always spin 2, green is spin 3. So that, I think that's what it is.
Yeah, you're right.
Any other questions? So this is what we believe, and a lattice calculations show that. But the presence of mass gap in a theory that classically has no scale in it is, in some sense, is a surprise. That's why it's called dimensional transmutation. So so that's the idea. And to prove this, rigorously is one of the problems I mentioned already by Clay Mathematical Institute, Young, Mills, and mass gap. So if you actually manage to show this rigorously mathematically, then you are supposed to receive $1 million. So I definitely encourage you to think about it. So that's the puzzle, and we think we understand it because we can do the lattice simulation. But certainly, it does lack a rigorous mathematical proof that a theory without any scale, dimensional for constant, would lead to a finite mass gap. So that's what we think would happen in Imperial-Mills theory. Okay, any questions about that? Good. And so now we would like to actually put the matter fields into it. And so to get some idea on how things behave when you put the matter fields, then I'd like to show you some sort of experimental the data that gives you the idea on what's going to happen in these theories. And the most of the data comes from this experiment called ALEPH. And ALEPH is an E plus E minus collider, which happened at CERN in the same tunnel where LHC is right now running. So if you look at this picture inside the tunnel, then, and some of you might have seen a picture of the LHC inside the same tunnel, and the accelerators, I believe, would look different to you because it's a different machine. And so instead of colliding protons on protons, this machine collided electrons on positrons at a center mass energy from 90 to 200 GeV or so. And ALEPH stands for, very creative name, Large Electron Positron Collider. So, what I'm showing you today is some of the events recorded by this experiment called ALEPH. So this is a typical collider detector, and the central part that gives you the tracking information is what is called a time projection chamber, which is a great invention in Berkeley by Dave Nygren. And let me just go ahead and show it. So I just like to give you some ideas on how event displays look like. So this is an event where you collide E plus E minus that produces what is called the Z boson in the standard model. And this Z boson decays into A plus E minus. And for all purpose of a discussion today, you can forget about Z boson. You can view this as E plus E minus going to photon, going to E plus E minus pairs, just like what you computed the last semester in QED. For all intents and purposes, that's sufficient for us. And so what you see here is that the pair of electron and positron is produced at this the collision point, and the produced electron and positron, because they are charged particles, leaves a track in this time projection chamber, and it produces a big hit in this first calorimeter, which is the electromagnetic calorimeter. And so this the yellow bars show the energy deposit depending on where you are looking at in this electromagnetic calorimeter. So if you see a track that shows the particle has a charge, if you see a big hit in the electromagnetic calorimeter, that's presumably either photon or electron. And knowing that there's a track, together with this hit in the electromagnetic calorimeter, this must be electron or positron. And it's hard to tell which one is which because these tracks are supposed to be slightly curved in the magnetic field. So, I'm sure the experimentalists knew which one is which because looking at the curvature of the track, but just by looking at this event display, it's hard to tell. But anyway, this is clearly an E plus E minus pair. Similarly, you see a track here, and so it's a charged particle, has a very minimal energy deposit in the electromagnetic calorimeter, so it's not electron. It also has rather minimal energy deposit in what is called hadronic calorimeter, that's outside here, but it shows this hit in the outermost layer, which is the muon chamber. So the muons are so penetrating so that it doesn't leave much energy throughout this detector complex, but it does show a hit in this outermost layer, which means that it's a highly penetrating particle, and hence this is a muon. So this is how the muon pairs look like. And the produced muons can also radiate in a photon. So this is a diagram where E plus E minus goes to photon, produce a muon pair, and one of the muons, either mu plus or mu minus, emits another photon. So that's a three-body final state, and that shows up in this peak in the electromagnetic calorimeter. So you don't see any track from the collision point, but all of a sudden you see these big hits in the electromagnetic calorimeter. So that's a good sign that this is a photon. And two other charged particles have hits in the outermost layer, so they have to be muon. Hence, this is a mu plus mu minus gamma event. And the reason I'm showing this to you is that we will see an analog of the QQ bar gluon event in a couple of slides. So you can have this production of fermion pair with one gauge boson radiated from the final state. So in this case, that's a QED radiation of photon. You can also see a QCD radiation of gluon. And so we'll come back and talk about that. But anyway, any questions about this kind of idea of the event displays? And E plus E minus events are so clean that you can sort of immediately tell what you're looking at just by staring at this event display. So that's really cool. Any questions so far? Okay, so of course this so far is in some sense an exercise. Now we get into the QCD bound states. And this is the first example where these states with a strong interaction come in. So in this case, what you see here is a track. Here you see the energy deposit in electromagnetic calorimeter, so it's an electron. On the other side, you see hits, which appear both in electromagnetic and hadronic calorimeters. So what you're seeing here are some charged particles which have hadronic interaction, namely strong interaction. So the interpretation of this event is the tau pair. So you produce tau plus and tau minus. Again, I don't know which one is which. And one tau decayed into electron and two neutrinos. So what you're seeing is the electron as a decay product from one of the taus. The other tau decays into a neutrino and a couple of the pions. And I think that I wrote this 3 pi, but I think this is actually 5 pi instead, because I see 3 tracks and they are charged. So they are pi plus and pi minus. But I also see a fairly big energy deposit in electromagnetic calorimeter. So presumably these are photons. So I believe there is also pi naught that decays immediately into gamma gamma. And gamma shows these hits. So this is probably something like 5 pion events from tau decay. So the point here is that once you produce these strongly interacting particles like pi plus and pi minus, they would show these hits in the hadronic calorimeter. So that's the main point of showing this event. And if you're not familiar with the standard model, it's totally okay, because what the main purpose of showing these things is just to show that the hadrons, strongly interacting particles, would hit those hits in this hadronic calorimeter, which you see in this event. So this is believed to be the production of quark and anti-quark. And each quark ends up in this, what is called jets, the spray of quite a large number of particles. And many particles show energy deposit in electromagnetic calorimeter. So that means that some of the particles are pi naught going to gamma gamma. And you also see many charge tracks which correspond to hits in hadronic calorimeter. So most of them are likely to be pi plus and pi minus, and some of these are strong interacting particles. The idea here is the following. So when E plus E minus annihilate, that produces a pair of quark and anti-quark. And when they're produced, they are very close to each other. So they are within the regime of this Coulombic potential. So that's no different from producing a mu plus mu minus pair, which also have the Coulombic attraction between them. And because the particles are produced so relativistically, the Coulomb attraction doesn't bind them together, so the particles start to move away from each other. But the difference for mu plus mu minus in this case is that once the quark and anti-quark become separated, as much as what corresponds to this energy scale where coupling constant blows up, lambda. So distance scale, which is inverse of lambda, in the case of the QCD would correspond to something like a 1 Fermi, 10 to the minus 15 meters. Once they are separated by the distance, now they start to feel this linear potential. So in some sense, when they're produced, the quark and anti-quark believe they are free particles. So they try to freely move away from each other. But once they are as apart as 1 Fermi or so, then all of a sudden realize that, oops, we're supposed to be confined. So they can't go any further. And the energy starts to grow linearly with the distance between them. So at some point, because the energy grows linearly with the distance, it becomes energetically favorable to produce actually a pair of quark and antiquark from the vacuum, so that each particle is now bound together with the one part of the pair you produced. So this Q bar is now paired with Q so that they become a gauge singlet combination. And this Q bar is produced out of the vacuum together with this Q. So that this Q is produced together with this Q bar. And this Q bar now binds together with this Q. So each of them now are gauge singlets combinations. But this leading particle is still moving fairly energetically. So the distance between what is produced out of this vacuum, which is a very soft, slow particle, and this leading particle that is produced from the annihilation that's really moving fast, this one is still moving far away from the other one. So at some point becomes, again, energetically favorable to produce another pair and another pair. So this, what is called the string attached between quark and antiquark starts to break up into smaller and smaller pieces until that produced particle and the original particle share sort of similar velocity now, so that this combination would actually move together as a bound state. So this is the process which is called the string fragmentation. So the produced pair has a string attached, and this string starts to fragment because this energy of the string grows with the length of the string, and eventually you end up with a bunch of short strings, and each short string corresponds to this bound state of a quark and an antiquark called a meson. So that's the idea of the string fragmentation. Sorry. So any questions about this idea? So this is believed to be the consequence of the confining theory.
One quick question though. So how exactly do you know that it's a Q bar pair that's going to be formed? Isn't there other possible combinations that can come out of the energy?
Well, let's see. So first of all, what you can measure is the identity of these particles. And so you can tell that these particles are mostly pi plus and pi minus. And pi plus and pi minus are spin zero boson. So if you would like to make up this pi plus and pi minus out of the quarks, then it has to be a pair of quark, at least two of the fermions, right? So because it's a boson. And you can also see, okay, maybe that's not the question you're asking. Andres.
No. That was the question. I think that makes sense because we're just matching with what we see experimentally.
But there's even better evidence that what we are staring at is really the pair production of quarks because of the following analysis. So as you can see, you can pretty well tell which direction the fermion was produced initially. So you see this spray of particles, but what you do is the sort of momentum weighted average of all of these particles to define sort of the average direction of the spray, namely jet. And you can compare that to just a perturbative calculation of E plus minus going to QQ bar. So the calculation is exactly the same calculation as you would do for E plus E minus to mu plus mu minus, at least at the leading order in perturbative calculation. And that would predict the angular distribution. So this theta is the relative angle from the original beam direction to the direction of the particle that's produced. And so this is just simply coming from the angular momentum conservation. So when you annihilate E plus and E minus, and because of chirality conservation, if you have electron with helicity positive, that's a right-handed electron, the only positron that can annihilate with it is the left-handed positron. So if you collide them together, you produce a virtual photon sitting at the middle, which should have a net spin 1. Which is, of course, natural for a photon. And when you produce the quark and antiquark, and to the extent you neglect the mass of the quark, which is a very good approximation at this high-energy collider experiment, again, there's a chirality conservation. So if quark is left-handed, then antiquark is right-handed. So overall, there's a net spin 1 along the direction of the produced quark and antiquark. So if you have spin 1 along the beam axis initially, You have spin 1 along the production axis. And if I rotate theta all the way to pi, then the final state spin would be opposite from initial state spin, which goes against the angular momentum conservation. So the amplitude should vanish in that limit. So this process, therefore, should have an amplitude that goes like 1 plus cosine theta, so that it correctly vanishes when theta goes to pi. And the rate is square of that. So this process should have the angular dependence of 1 plus cosine theta squared. And certainly, both initial state and final state particles can also have the opposite spin orientation. So if, let's say, initial state has opposite spin, then the amplitude would be rather 1 minus cosine theta, and you square that. And if you add 1 plus cosine theta squared and 1 minus cosine theta squared, the sum is 2 plus 2 cosine theta squared, and therefore angular distribution is 1 plus cosine theta squared. And this is 1 plus cosine theta squared in dashed line. These are the data points, and they agree extremely well. If the produced particle were spin 0 particle instead, then initial state has this spin 1 along the beam axis. Final state particle doesn't have any spins. So both when theta goes to 0, the initial state with spin 1 would go to spin 0. That shouldn't happen. So amplitude vanish. When theta goes to pi, again, initial state has spin 1 along this direction, but spin 0 in the final state. That shouldn't happen. So this should vanish both for theta equals 0 and theta equals pi. Therefore, the amplitude should be sine theta. Rate should be sine squared theta. And that will be the prediction for spin 0 final state. And that clearly doesn't match the data. So this way, you can actually see, just by looking at the overall directional dependence of these jets, you can tell that this sprayer particle actually originates from spin 1/2 object. So that's how we know that we are really producing quark and anti-quark, which ends up in a spray of particles or jets because of this string fragmentation business. But what was produced initially, really, we know is spin 1/2. Okay, any questions about this?
Thank you. That makes sense.
Okay, good. And then you can also go ahead and look for the analog of mu plus mu minus gamma I have shown earlier. But in this case, it's the QQ bar where either quark and anti-quark radiates a gluon. And gluon would become its own jet. So that's how you see these 3 jets in a single event. And again, the angular distribution of these the jets will tell us something important. So if you think that you have produced quark and anti-quark, as we have seen on the previous event, but radiated something else, you can ask the question, is this a spin 0 particle or spin 1 particle? And again, angular distribution will tell them apart from each other. So this, the red dashed line is the emission of spin 1 object, vector gluon, together with this fragmentation of the string. And the difference between this green curve, which you predict just by the perturbation theory from QQ bar gluon, the angular distribution, to a simulation which has this effect of string fragmentation in it, you predict this the red dot dash line. But in the case of emission of spin 0 particle, which is called the scalar gluon here, then again, you can define a Feynman rule of QQ bar scalar coupling from Yukawa interaction, and you can do the fragmentation on top of it. You will predict this curve, and clearly the data agrees with the spin 1 gluon instead of spin 0 gluon. And so this horizontal axis is the kinematic variable, and x2 and x3 are energy fraction of the jets relative to the overall center of mass energy in the event. So this kinematic variable just happens to be most sensitive to the difference due to the spins. So this is the way you know that there is actually spin 1 particle, which fragments. And so that's the evidence of the existence of gluon. So this is how we know that this is indeed a theory with the spin 1, which then have to be a gauge theory in order to have a description without redundancy. So this is basically a proof that we are looking at a gauge theory. Any questions about this?
This is backing up a slide, I guess, but how many, so based on the cartoon picture of the fragmentation, I would think that there would need to be like 10 to the 15 fragmentation events or something, since this is like the actual collider is like human scale, right? Like these pictures are, but it doesn't look like there are like, are each of these distinct lines a single fragmentation event, or like how many,
So each line corresponds to this meson. Some of them are protons and neutrons, but most of them are mesons. So each line would correspond to this.
So there are really only 6 or 8 fragmentation events?
Oh, you're talking about number of particles. The typical event at this energy scale, if I remember correctly, is something like 20 particles. And you're not seeing actually all of them. Some of them are too low energy to be detected. Some of them are neutral, so you don't see a track. Instead, you see these hits in electromagnetic calorimeter. For example, here you see hits, but you don't see any corresponding track. So this is presumably pi naught.
Okay.
So altogether, on average, there are something like 20 particles coming out of the string fragmentation.
Okay, so these are, okay, I see. Okay, thank you.
Any other questions?
So if you did want to estimate how many fragmentations could occur, would it be roughly correct to just like order of magnitude estimate? You just take the energy on the beam axis and divide it by the energy of a meson? Would that be
Actually, that's not the case. That's not the case, because each meson is also moving with relativistic energies. So if you just do the division of the beam energy by the scale of the confinement, then you are basically assuming that each combination is modest at best, right? But they are still relativistic.
Okay.
Right? So the kinetic energy takes chunk of the original beam energy. So that simple fraction is not supposed to give you the number of particles. And actually, you can actually develop a theory for this. I'm not going to get into this, called the fragmentation function, which means that how many particles get produced in what type out of a given initial pairing quark. And the number of particles produced as a result of fragmentation goes only logarithmically with the energy of the beam. So that's something you can also compute based on the QCD perturbation theory. You can write out a prediction on the total number of particles produced, and then you can, it's difficult to predict the absolute, the scale of the total number of particles in perturbation theory, because this really has to do with this, the confining effect. But the QCD would allow you to compute how this expected number changes as a function of energy scale. And that's something you can predict out of QCD in perturbation theory. And the prediction is that it grows logarithmically with the energy. And I don't have the data on slide today, but I can show you if you're interested later on that data really does show that the number of particles produced changes logarithmically as a function of energies. Does that answer your question?
Yeah.
Okay, good. So this is the way we know it's actually a gauge theory. And in addition, we know it's a non-abelian gauge theory. So this is 4-jet events. It starts to look pretty messy. But anyway, so this is the idea that this is QQ bar with 2 extra the colored particles produced at the same time. And there are several possible diagrams for this. For example, you can produce at least 2 additional gluons from the quark legs, from each leg or from the same leg. And this is non-abelian gauge theory. So each of the quark and antiquark produces a gluon, and gluon then splits into 2 gluons. So this is possible only in non-abelian gauge theory. You can also produce a gluon which splits into QQ bar as well. So looking at the angular distribution of 4 jets, then you can try to sort of separate these different contributions apart from each other. Only on statistical basis, you can do an event by event basis, but you can try to extract the contribution of each of these possible diagrams. And so this one corresponds to the Feynman diagram. When you take the square, you sum over these final state quarks. So that corresponds to TA matrix, closing another TA matrix. So this diagram is proportional to this Dinkin index for the fundamental representation that gives you a half. On the other hand, this one, when you take a square and sum over all the gluon colors, and that will correspond to the trace of matrix in the adjoint representation. Therefore, that is what is proportional to C2 of G, a dual Coxeter number. And phenomenologically, people refer to this as CA for the adjoint, and refer to this as TR, which I think corresponds to trace. And so you can extract TR and CA out of the data relative to the dominant contribution which comes from this, which is proportional to CF, because you take the square of this Gluon TA matrix along the Quark line is multiplied by TA. So TA times TA sum over A is Casimir called CF. In the case of SU3 gauge theory, CF is 4/3. TR by definition is 1/2, and CA for SU3 is 3. That correspond to this point. And what you're seeing here is out of this experimental data of 4-jet events, you can extract CA over CF and TR over CF, and this is the 95% contour, and this is SU3 gauge theory. So that's how we know that the strong interaction is indeed non-abelian gauge theory. And this non-abelian vortex had been first discovered by Tristan E plus minus experiment in Japan, and the previous 3-jet events had been first discovered by E plus E minus machine Daisy in Germany. So all of these things have been discovered in E plus E minus experiments. So based on these data, now we know that it is a non-abelian gauge theory, and in particular, it better be SU3. So that's how we can extract the information on the underlying gauge group based on experimental data, and that's what we sort of expect that should happen in any of these confining non-abelian gauge theories. So again, there's no proof that this is the case for arbitrary non-abelian gauge theories, and even lattice calculus have not been done for every single non-abelian gauge group, so we have only limited information and evidence, but this is how well we are convinced that this confining dynamics is what's going on in non-abelian gauge theory. Right, any questions about this?
It seems that the point also lies in SP4 and SP6.
Right. Yeah, that's why I didn't say this tells us it's SU3, because some of the other groups are sort of on the edge of the preferred region. But there are also some other evidence, like running coupling constant. And this is, again, the measurements of the size of the coupling at many different energy scales of the measurements, and over more than 2 decades of energy scales. And this black curve is what gives you the prediction of the QCD SU3 gauge theory. And the data points lie really on top of the predicted curve. So this is can be viewed as an evidence that this is indeed SU3 instead of other groups like SP4, SU4, and so on, which was still sort of allowed within this ellipse. But this would really uniquely points to the SU3 gauge theory. And in order to do a fair consistency check, whether all of these measurements are really saying the same thing, is by doing the following exercise. Take a measurement of some energy scale, in this case is tau decay, and tau can decay into neutrino and QQ bar. QQ bar can also radiate a gluon, and so that the gluon emission has information about the size of the coupling constant in tau decay, and so that you can extract that from the tau decay rate. And so that's how you extract this data point at the tau mass, that's 1.777 GeV. So what you can do is to take this measurement and then run the extractor value to the energy scale of the Z boson, that's 91 GeV, using this curve. So you take every single measurement on this curve and take the measurement at that given energy scale and translate that to what will be the corresponding coupling at the common energy scale, where you can compare against them each other. And this is how they look like. So, some measurements are more accurate than the others, but once you actually take them, all the measurements to the common energy scale for comparison at the Z boson energy scale, and they are, are really consistent with each other. So this is the way you know that we have a good understanding of what's going on based on SU3 gauge theory coupled to quarks in the fundamental representation with 3 colors for each quark. And so that's the way we now think we understand the dynamics of the non-loving gauge theory when you can apply perturbation theory to it. And of course, it still remains to be understood what exactly would happen to quarks when you go to long distances and lower energies. And I'll talk about that in a moment. But any questions about the sort of the basic understanding of how perturbative description of non-loving gauge theory seems to work and to describe the data? Okay, it looks like everybody's convinced. I hope that's the case. And that agreement is also beautifully demonstrated in this plot. It's in the ALEPH experiment. So now you're going to even much higher energy of 13 TeV compared to 91 GeV. And then what you're looking at is again jets produced out of proton-proton collision. And I don't go into much details about this. That's a subject of discussion, I hope, in Lawrence's class. Is anybody taking Lawrence's class? Did he discuss this kind of pattern distribution function in
Yeah,
QCD?
he discussed it a few weeks ago.
Okay, good. So the way you actually end up computing these processes is to first look at what particle is contained inside proton. So this is an idea called parton inside proton. So that's a part of the proton. So parton I, like quark or gluon, resides inside a proton with the energy fraction x. So if the energy of the proton in this case is 7.5 TeV, x times 7.5 TeV is the energy of this parton, which carries only a fraction of the total energy of the proton. And so this F parton distribution function tells you the probability of finding this parton I inside a proton with the momentum fraction x1. And same thing for the other proton. This is the parton J inside the proton with the energy fraction x2. And then you fold this to the cross-section of these two partons, I and J, leading to some final state x. And so this is the probability with the momentum fraction x, so you have to integrate over this momentum fraction to get the total probability, which gives you this cross-section. So what this plot is showing is the beautiful agreement between the data points shown in circles and boxes with different cuts, or what is called rapidity, which is basically the direction of the jets produced inside this detector, compared to the horizontal bars that are theory projection over some 9 decades or something. So this is how well the perturbative calculation of this cross-section would agree with the data. And so in order to actually lead to this kind of precision in theoretical calculations, then you have to typically go to next leading order, or sometimes even to next leading order calculation. So leading order is a 3 level, next leading order is 1 loop, next leading order is 2 loop, and this is a humongous undertaking. And just to tell you how humongous undertaking this is, let's just take look at the Feynman diagrams, which you need to compute for, let's say, glue inside these protons to go to 4 gluons in the final state. So let me switch to the list of Feynman diagrams and share the screen of the Feynman diagrams. Can you see Feynman diagrams?
Yep.
Okay, so this is the Feynman diagram of 2 gluons going into 4 gluons in final state. So you see these diagrams, more diagrams, more diagrams, more diagrams. There are quite a few, so let me just zoom it out and show more diagrams, more diagrams, more. And so up to this point is the next leading order. There are 220 diagrams at the tree level. And I mentioned sometime earlier that the non-abelian gauge theories are sticky. What I meant by this is the gluon would couple to itself, sticks to itself. As a result, the number of Feynman diagrams is huge already at the tree level, 220 of them. If you go to next leading order diagram, so that starts from here, okay? And this is diagram 221. And then you keep going. And it will take forever because I have 606 pages of PDF. So let me scroll all the way to the bottom. And some diagrams, of course, include the Faraday pop of ghosts. And you see the number 9045 at the next leading order. So this is how sticky gluons are. And the attacking this problem of computing Feynman diagrams is a formidable problem. So let me go back to my slides. Okay, where is it? So that's what you have to do to produce these horizontal bars. So obviously, computing these Feynman diagrams as just diagrams is not the way you can approach this problem anymore. So this is the set number of diagrams I mentioned. And so what you actually have to do is to become more clever than just doing Feynman diagram computations. That's clearly not practical. So in order to actually compute this, and this is really getting into this sort of active research area, which is happening still now, is to go something clever. So it turns out that when you actually compute this glue to glue amplitude, but if you put additional particles into it, namely you put in 4 wire fermions in adjoint representations called gluino, and 6 real scalars in adjoint representations, then theory becomes a supersymmetric. In particular, we have a large number of supersymmetry, 4 of them. That's the maximum number of supersymmetries you can have in 4-dimensional gauge theory. And once you actually make this theory much bigger to make it supersymmetric, it turns out that there's so many theoretical constraints because of symmetries, you can actually get a very good handle on this, what this amplitude should look like. But of course, there are too many particles in it. So out of this n equal 4 supersymmetric theories, you first determine this amplitude in that limit, and you start to subtract additional contributions you don't need in QCD. And subtraction would correspond to loops of this fermion in adjoint representation and scalars in adjoint representation, which are far easier to deal with than the loops of the gauge bosons, it turns out. So that's why it simplifies the problem somewhat. But you still have to face large number of fermion and scalar loops. And that's when you resort to another technique where you start to rewrite each momenta of these particles with spinors, actually, called a twister technique. And then they divide up the loops into the imaginary parts with the unitarity cuts. And once you determine the imaginary part, you can translate that into real part using analyticity of the amplitude. So a lot of techniques actually go into this kind of calculation. And this article I actually learned from my colleague, Murat, actually has the description of all of these techniques that go into this. So, so that's how you can compute the amplitudes. In addition, you also need to understand this Poisson distribution function. And this Poisson distribution function actually obey what is called the DG-ALEPH equation. It used to be called Alter-Ray-Paris equation, but it turned out that there are also Russians that did something similar earlier. Dokshitzer, Gribov, Lipatov, I think. And so it's now called DG-ALEPH equation. And what this equation tells you is that how a given Poisson distribution function can change as a function of energy scale, because if you change the energy scale, you are changing the resolution of your measurement. And once you go to higher resolution, one parton may split into more partons like this. And this splitting process is something you can compute in perturbative QCD. And next leading order computation of this splitting function have been achieved only less than 6 years ago. So this is, again, pretty much still a work in progress. And there's still many processes have not been computed at levels of accuracy. And even if you compute all of this calculation in perturbative QCD, you have to then relate what you computed to this shower of particles in jets. So you have to go through this yet additional process called hadronization, namely that you produce these partons. The partons move away from each other, so then the strings attached between them, they fragment into more hadrons, and so this process is definitely non-perturbative. So how we deal with it is basically purely empirical. So we can't really predict it based on perturbation theory, but because we already have wealth of data, especially from ALEPH, on how this hadronization process from string fragmentation happens, you can try to sort of model that based on empirical data and apply that to the high energy experiments at the ALEPH. So you need to combine all of these things to produce this beautiful agreement I showed earlier. So even though this looks like a simple plot, there's so many things go into this. And at the end of the day, we still need to understand how the parton distribution function would arise from non-Navier gauge theory. Right now, this is a description, empirical description, which is based on data, but no first principle prediction on it. We do have first principle, the prediction on how this parton distribution function changes as a function of energy scale. That's this DG-ALEPH equation, but we don't know what these are supposed to be from the beginning, and that's not something we can predict. And how hadronization works and this fragmentation works is again a description. Again, you can predict how that changes as a function of energy scale, very similar equation to this one. So change can be predicted, but not the function itself. So, so this is still sort of a combination of half empirical, half theoretical, and it's technically a very demanding subject. And that's why there's a lot of research is still going on today. So any questions about this?
The cross section is also that also comes from diagrams, the sigma ij to x term, not just the parton distribution.
Right. So this sigma ij to x is definitely something you can compute in perturbation theory. For example, let's say you pick one up quark from proton and one gluon from the other proton, then you can compute up quark colliding with gluon going to, let's say, another up quark and the down quark, anti-down quark plus gluon, something like this. So you can predict this cross-section in perturbation theory. And you fold this prediction with this parton distribution function, which you measured at some low energy scale, and you evolve that to the energy scale of interest, like at the ALEPH, using this DG-ALEPH equation. So that's how you know this function empirically. And then fold that together to compute the cross-section going to the final state X. But the final state X, so far, you have predicted still at the level of parton, namely you're looking at, in an example I mentioned, UDD bar gluon, that's X. But what you observe in the experiment is shower of these bound states. So you have to connect this partonic final state to hadronic final state somehow. So that's when you have to fold this further with the fragmentation function and make the prediction on the hadronization, again, based on the empirical input we have learned from the lab data mostly. And only after that, you can compare that to what you measure in the experiment. Does that make sense? Okay, go ahead.
Go ahead, Max.
Max? Hello?
Oh, sorry, I accidentally muted myself. What,
okay.
I think I just missed it the first time, but what cross-section is actually on the y-axis here?
Y-axis is actually what is called the inclusive jet cross-section. So here, the experimentalists are not asking the question about what kind of jet you're looking at. So jet may come from WDK or just a gluon or quark. So here, they are trying to be very agnostic about it. So just the fact that they have seen a jet, and they plot the number of jets as a function of what is called the transverse energy. That's the energy of the jet perpendicular to the beam axis. And so that's this data points here.
Okay, thank you.
Okay, Ciao?
Oh yeah, so you said that computing Feynman diagrams is hard, but I imagine that these are all done by computers, right? So 8,000 diagrams shouldn't be a very hard task for a computer, right?
It is still a very hard task. And that's partly because, first of all, you have to do renormalization. But it turns out the more difficult thing is what is called the collinear and soft singularities. So if you have this kind of a process of multiple gluons in the final state, and let me go back to the Feynman diagrams. Once you see these two gluons in the final state, which are more or less going along the same direction, then in the limit where the relative angle goes to 0, then the cross-section diverges. That's what it's called a collinear singularity, because the two gluons are collinear in the same direction. Also, when one of the gluons whose energy goes to 0, then that also diverges, called a soft singularity. And because you have 4 gluons in this case, in principle, 3 gluons can be collinear, and 2 of them can become a soft. Then using dimensional regularization, that actually gives you 1/epsilon 4th pole. And that happens only in a very limited area of the phase space integral of the final state. And that's not something computers can deal with. You have to very cleverly isolate these singularities out of this 4-body phase space, which is 12-dimensional, I think. And so to isolate these singularities, and these singularities are supposed to be canceled by the loop diagram, which interferes with tree-level diagram. And so that whole machinery of how to regulate this infrared and soft singularities are very, very complicated, and it's still not really automated. And one of the things, for example, Christian Bauer at LBL is working on is to try to sort of automate this process by using a technique called soft collinear effective field theory, and still, again, work in progress.
Thank you.
Any other questions? Yeah, so basically I'm trying to tell you here is that the level of work that goes into this kind of study of a strong interaction on non-abelian gauge theory is actually pretty enormous.
So just at a high level, are the most accurate results from this kind of sort of semi by hand Feynman diagram calculation, or from lattice QCD? Or is it they're accurate?
The lattice QCD is actually rather ineffective for these high energy processes because they are intrinsically Minkowski space processes, and lattice gauge theory can be done only in a Euclidean space. So ultimately, for example, this Poisson distribution function of probability of finding a particular quark with particular momentum inside a proton is a really sort of confining dynamics and should be predicted by the lattice QCD, but it's nowhere close to that.
Huh, okay.
Okay, so anyway, so that's what it takes to actually even do perturbative analysis of the non-abelian gauge theory. But now we'd like to get a better sense on what happens non-perturbatively at long distances in the QCD-like theories. So we know the Lagrangian, and it's a single line, so we know exactly how it looks like by now. And you can think about this theory in many different possible gauge groups and many number of flavors of the quarks in the fundamental representation. So these are collectively called QCD-like theories. And for the sake of discussion, let's talk about the massless limit where the quarks don't have a mass. And that's actually pretty close to what we know as the realistic QCD, because the mass of the quarks, up, down, strange quarks, 3 of them, are much, much lower compared to the strong scale lambda. So as a 0th order approximation, you can neglect them. So talking about this non-abelian gauge theory with matter fields that are massless is a good approximation to what we think is the theory of strong interaction. And once you take the massless limit, you don't have this mass term. And this kinetic term for the fermions would break up into 2 pieces, depending on the chirality of the fermions, namely the eigenvalues of gamma 5 matrix. So 4-component Dirac spin-up psi breaks up into two components, which is left-handed, where gamma 5 has eigenvalue -1, and two other components where the eigenvalue of gamma 5 is +1. So the kinetic term breaks up into these two pieces, with each of them with NF quark, what we call flavors. So they become in NF species. So as a result, this Lagrangian has this UNF cross UNF symmetry, namely that you line up NF of these left-handed quarks into a column vector, the NF dimensional column vector, and you can freely rotate this column vector by a NF by NF unitary matrix, UL. This is a global symmetry. It's not a space-time dependent. It's a global symmetry, so that this kinetic term doesn't change. So you have this symmetry. And for the right-handed fermions, you also have the similar symmetry of rotating this NF dimensional column vector by an arbitrary NF by NF unitary matrix UR. So that's the NF by UNF left by UNFR symmetry. And this unitary matrix for rotating left-handed fields and this unitary matrix for rotating right-handed fields are totally independent from each other, hence UNF but UNF times UNF symmetry. So the minute you have NF massless quarks in SUN gauge theory or any other gauge theories, you have this UNF cross UNF symmetry. So this symmetry gives us a key to understand what would happen at long distances, because as we have learned in the discussion of critical phenomena, at long distances, symmetry is always the key to understand what's going on. So the first question to ask is this theory confining? So I define the autoparameter of the confinement to be Wilson loop, whether that is a area law or perimeter law. And perimeter law refers to the situation where Wilson loop is damped exponentially by the perimeter, basically the length of the loop, so circumference, instead of the area. It turns out that this QCD-like theory does not exhibit area law, but exhibit perimeter law, which is similar to the idea of the string fragmentation. So this Wilson loop was supposed to be the way of measuring energy when you place a very massive static source of gauge boson, so here and there, and separate them over distance L. But if L is large compared to the confinement scale lambda, then energetically, it is favorable to pop up a pair of quark and antiquark out of the vacuum. That's this, the pink line, so that this quark is now paired with this light antiquark that came up from the vacuum. This antiquark, heavy antiquark, is now paired up with the quark that came from this from the vacuum, so that each of them are now bound states. You can separate them without causing a string to become long. So as a result, the energy of this system is basically given by this distance of the string and that distance of the string, and is independent of the overall length L. So as a result, this energy goes only with this string length times this time interval, and that's m times t piece in the exponent. And because it's a Euclidean theory on the lattice, then if there's a time dependence, there must be also corresponding the spatial dependence. So at the end of the day, the Wilson loop behaves linearly with the circumference of the loop instead of area. So strictly speaking, the theory with the matter particles, massless matter particles, are not confining because it doesn't lead to the area law. But very loosely speaking, theory is still quote-unquote confining because it's not that you can really separate this quark and antiquark away from each other. The only thing you see are still these bound states. So we still call this confinement in loose sense. But strictly speaking, it's not the area law or Wilson loop. And what do we expect in this kind of theory? It is the emergence of these bound states. And bound states are supposed to be singlet under the gauge group. So if we have a quark and antiquark, then you can build mesons, just like what we have seen in the case of the real-world QCD and experimental data. And you may also have this combination using this epsilon tensor to contract the gauge indices. So in the case of QCD with SU3 gauge group, this epsilon tensor runs over the number of colors. So this is epsilon ijk, and 3 quarks to contract the indices. And so you expect bound states made of 3 quarks, and that's what we believe what the protons and neutrons are. And these baryons can exist in SUN gauge theory, SON gauge theories. SB groups don't have this epsilon tensor as invariant. So depending on what groups you're looking at, you may or may not have baryons, but mesons always exist in all of these gauge theories. And it's a little counterintuitive, but if you have, for example, SU4 gauge theory, the baryons made of 4 quarks instead of 3 quarks. So the baryon is actually a boson in SU4 gauge theory. So that it alternates between even NC and odd NC, whether the baryon is boson or fermion. And in addition, you may still have Glueball because it's a gauge invariant after all. You may also build gauge invariants out of 2 quarks and 2 antiquarks called tetraquark. You may also have pentaquark in the case of QCD, 4 quarks and 1 antiquark, for example. If you have SU-NC gauge theory, that would be NC plus 1 quark and 1 antiquark. So I don't know how to call that whatever quark in Greek, but anyway, so you may expect that kind of bound states as well. And the question is whether such things exist. And again, going back to the real world QCD, we have these 6 quarks. We have now determined their masses to some level. It's very difficult to determine the masses of these quarks when you cannot liberate them. So there is actually also complicated theory that goes behind it. But the whole point here is that these 3 quarks have mass much lighter than strong scale lambda. That's of the order of 300 MeV. So even the strange quark is less than a third of that. So we can safely take the limit where these masses go to 0 as a zero thought approximation. On the other hand, these 3 quarks are considered to be heavy, much heavier than 300 MeV or 0.3 GeV. So we have 3 light quarks and 3 heavy quarks, and they are all kinds of the bound states you see in the data, and we know pretty well what they are actually made of by now. And so these are states made of all these quark constituents, and they're also states that are made of B quark and anti-B quark. There are no bound states of top quark because the top quark actually decays within like a 1 GeV width that correspond to 6 times 10 to the minus 25 seconds, which is faster than the time when top quark can reach this confining potential. So the top quark always decays before it gets confined. So there are no bound states of top quarks ever observed, but all the other bound states have been observed. And all of these states are believed to be mesons, except a few exotics, which are called X and Y and Z in the particle data group. And so I already talked about most of these mesons can be understood as the bound states of the massless constituents in a linear potential because they exhibit this linear relation between m squared and j. So this part is sort of makes sense. And these are the bound states made of charm quark and anti-charm quark. And because charm quark is heavy compared to strong scale, then this is sort of a non-relativistic hydrogen-like bound states. And you can even specify this bound states in the spectroscopic symbols you use in the atomic physics. So most of these states can be understood as the CC bar bound states. But here that shows some of the states in red, which are exotics. And that they are still not quite understood. But one of them is fairly convincing. So this state, at the topmost state, Z, 4430 MeV, this state has a charge, but decays into CC bar bound state called psi. So this state or that state, which is known to be CC bar bound state. So clearly this state contains C and C bar in it, but has a charge. CC bar state charges cancel, so that's not CC bar. So the best guess is this state is CC bar UD bar. And these states started getting discovered rather recently in this millennium. The first one was observed in 2003. Became very clear that these exotics cannot be explained as a meson state only like 4 years ago. And it's still not clear what this state is. So one idea is tetraquark UD bar CC bar state. Another idea is it's the bound state of bound states, namely UC bar state and D bar C state, correspondingly are called D mesons, and two D mesons are bound together called molecule, and we still don't quite know. And that is QCD is still having a hard time computing the bound states of 4 quarks in it. And if you're talking about molecule, then you have to produce these two bound states and ask about interactions between them. That's also more difficult to do. So these states start to emerge experimentally, but we're still not completely sure what they actually are. And you can consult for example, this article talking about these exotics. So in general, if you have non-near-beam gauge theory, you do expect some of these bound states as well, and whether they really exist in nature or not, whether they can predict it out of the non-near-beam gauge theory is still an open question. Okay, I think I stop here. And what we would like to talk about very briefly on Thursday is that how well we can understand the long-range limit, long-distance limit of these theories for various choices of the gauge group and various possible number of the flavors. And so that has to do with this idea called the chiral symmetry breaking. But anyway, let me stop here. Any questions?
I have a question on that.
Go ahead.
The parameter law for the Wilson loop.
Mm-hmm.
So I guess after a Wick rotation, you end up with an imaginary part to your energy.
Right.
Is that basically describing that this is going to decay? It's basically like the fragmentation that we'd expect.
Yeah, that's correct. That's correct. But in order to compute fragmentation, you need to produce many sort of bound states in between, which means that you have to insert many operators somewhere here. And even the supercomputer allows a lattice simulation up to the lattice sites of something like a 48 or something like this. You know, once you take the fourth power of it, that really is a big number. And link variable connect each of these lattice sites, so that's even bigger number. So making the lattice big is extremely computing intensive. So the best you can do is still less than 100 or so. And inserting many operators in between is already a very difficult thing to do because of that limitation. And then further, going to a Minkowski space by another continuation is a very noisy numerical calculation. So we are still very far away from really computing fragmentation process.
I see.
That's why this is still a major research subject. Anyway, thanks for the question, Nick. Anything else? Okay, so as usual, I recorded this. Oh, did I record this? Maybe I forgot. Oops.
Yeah, I think it was recording.
Oh, okay, it is okay. Good.
Good.
All right. So I put up the video on the YouTube and also make the slides into PDF and post it on B courses. And also I promised to post a new homework problem later today. Okay, so see you at the office hour.
Thank you.
Thank you.
Bye.